Most of the slides I've got here are original 35mm that's been scanned, so they really are period photographs. So you will find that there are some differences between some of the slides when it talks about the specification and the aim of the projects and things like that. As time went on, we actually improved what we were doing, which is unusual, but it's for the same reason John says Fujitsu never quite told us the truth. They always held things back. So the Fujitsu collaboration, this is the overall collaboration, was extremely successful. It consisted of the CMOS 8000 chips you just heard about, the S3L cube, of which we used 120 chip types, but we did not design all of those. We picked up about 16 of them from Fujitsu by taking the ones that they'd already designed and saying, well, they're generally useful chips, you know, which like a register chip and things like that. No point was redesigning those, and we designed the remainder ourselves. And we used 10 printed circuit boards, of which only 6 were in the cube, 6 for carrying chips, plus 2 side panels, 8, plus the store and Macrolan and Ethernet boards that were common between DM1 and S3L. We used swallow disks. Swallows were rather tiny, only 300 megabytes. We used Eagle disks, which were either 2.5 or 5 gigabytes, depending on which one you took, and we used their tape system. We evolved both the DM1 and the S3L out of the Nikos family of designers. So it really started in 2960 and moved through to 2966, 2988, 2958. And the development routes went down that path. So we took a reasonably well-known design and generally updated it by improving its functionality and improving the performance, the speed. If we look at the cube technology now, which was used in S3L, these are the features. So we're going to do, this was for a central mainframe application. We're going to run it at 7 million industry MIPS per second for a processor. Now, we did actually do better than that. That was based on the original Fujitsu estimates. We're going to use the most up-to-date technologies, Fujitsu ICL for the processor, the multiplexer, and the memory control unit, and CMOS, again from Fujitsu, for the IOC, the IO controller, input-output controller, and for the memory, the main memory. It's going to be a single cabinet per node. It's going to be completely air-cooled, not this liquid cooling that other people were using. We're going to build 800 systems over 5 years. As you'll see, we easily beat that as a target. But all our costings were all based on doing 800. We're expecting to do a product approval trial on first customer shipments in June '84, and the current status at this time, you will notice is mainframe systems development division. So this was right at the very beginning when we were guessing what we could do, and we had an aim of doing it by September '84. As you'll find out, we did it by '85. It was going to support VME and 2900, and 1900 emulation was going to be provided by, and we were going to put George 3 onto our machines. And the whole thing was going to be fully microcoded, so we could easily change it if we needed to. That's the Fujitsu technology. This is what impressed me when I went out to Fujitsu. I mean, there are the logic chips, those little towers on are for air cooling, because the whole thing is air cooled, and air is drawn into those boards which are mounted horizontally through them. And that's a RAM chip, which can either be 4K or 16K. And it's either 5 or 10 nanoseconds, depending on which size you choose. If you're using cache memory, you'd use the 4K. If you're using secondary cache, you'd use the 16K. We used 120 chip types in total. About 800. Fujitsu originally said this was a 400 gate chip. It turned out to be 800 and it ran at 0.3 nanoseconds a gate, so the gate delay was very low. And we achieved, throughout the whole logic period, with air cooling, a 29.5 nanosecond clock cycle. The interesting things about this is, when I went around the world, there were other people with the same types of technologies, achieving those sorts of capacities at those sorts of speeds. But nobody else could get anywhere near that 29 nanosecond clock time. And the amazing thing about it was that their printed circuit boards were half the size in both the X and Y directions of everybody else. So that printed circuit board was actually a quarter the area of other printed circuit boards. So of course you could pack all the chips a lot closer together. And the time delay from there to there was a half of what it was. So we've got 25%. Because half the delays are in the chip and half is in the wiring, if you double the speed through the wiring, you get 25% faster clock speed. So I said to Fujitsu, how on earth do you manage this? And they said, well, we used to have a clockwork watch division. And it was full of instrument mechanics who were used to working in very fine tolerances. And as you know, they said, we never have the industrial problems that you do in Britain. We always retain all of our employees. Therefore, we had to search for something for these clockwork instrument mechanics to do. And that was the printed circuit board that came out of it. And and that's quite a lesson to you. The tolerances on that cube, which is about 12 inches by 12 inches by 12 inches roughly, is certainly from that corner to the corner down there, is like a 20-inch internal diagonal. The tolerances on the assembly of that it had to be no worse than 2 thou in error. If you work that out, that's phenomenal. 2 thou in 20 inches. And they measured every diagonal. When we got them in West Scotland, we measured them because we had all the equipment that comes with these. And there was never one that was worse than 1 thou. They had to, because they had to achieve all the pins down the edges of these boards, all slid into zero insertion force connectors. Absolutely amazing piece of construction. All put together with Allen screws and everything was correctly torqued and everything. A magnificent piece of engineering. So, we used high-speed ICL logic, 400 gates per chip, which as you've seen is 800. 350 picoseconds, which came down to 300 as time went on. 76 logic pins. The RAMs are 6.5 nanosecond access. The MCCs are 14 layers, so those multi-chip carriers, the ones with the chips on, 14 layers, of which 8 layers are signal layers. So there are 4X and 4Y, and there's some of them go diagonally. So you don't just have to go on X and Y, you can also go on diagonals. And the MCC's got 1152 pins on it, half along each edge, and the zero insertion force connectors. And now literally, a board slides in like that, you press the things on the end, and they roll down, and they make a perfect connection. The side panels are the things that contain the mating halves and zero insertion force. 13 MCCs were the maximum. S3L was designed using only 6, with a 7th one for an optional floating point unit. It was forced air cooling. So the collaboration was that ICL had to design the chips, the MCCs and the side panels in the UK. And and that would use a combination of ICL and Fujitsu design automation. So we had to merge the two design automation systems, have interfaces between them so that we could do the design and do it so that it interfaced properly to Fujitsu's factories. Training in Japan, and clearly the engineers working on S3L had to understand the technology, they had to understand the design automation systems, and they had to understand the system and rework, system test and rework. Because not only in West Gorton we have the Fujitsu cubes, if we needed to modify anything, then we had to have the ability to modify it. And every one of these, as you'll see later, came with a whole set of rework equipment for actually removing chips, reassembling things, putting on wires and everything. It was all automated. So we sent our engineers over stage 1 in November 81 and stage 2 training in February 82. And this was like 25 engineers going out to Japan on each of those stages. And we had to build the bridges between the design automation systems. So in West Gorton we've got ICL mainframe systems that run our side of the DA and all the design capture and all the DGen, the diagnostic generation, and all of the test tools and all of the simulation. But also in West Gorton we've got a Facon 190, which was a Fujitsu machine that did the capture that they needed for the chip designs. We had an M380 in Japan that was going to do the tracking of all of the MCCs and side panels, and that was going to have to feed back to us, which we'll see in a moment. Now Hiragori, who said before was head of mainframe systems, he was concerned that the ICL engineers were working too hard and his engineers are tired. I got told that please tell them to go home because no Japanese engineer was going to go home whilst my engineers were still there. So, I mean, John spoke about, you know, they could ring you at midday, but it was not, I mean, because we were there, we were working. They all felt they had to stay with us. It's a funny situation. But it's all led to extremely good relationships. Anyhow, we then came to a set of detailed agreements. We clearly had to thrash them out, Fujitsu and ICL. Then we're going to join them, we're going to sign them. We had to do agreements for prototype systems and for pilot systems for covering the various printed circuit boards and the chips, the release schedule, the cost of what it was all going to cost, and the plan, the rate at which we needed them built by when. There's the rework and test equipment that they had supplied to us as part of this deal, covering all of the printed circuit boards, and I'll show you what that is in a minute. And then we had to have the manufacturing and supply agreement, which was all the production cubes, how, when we were going to release those, and the volumes and pricing of those by year. And altogether, I made over 50 trips to Japan at the last count. And as John said, it's a long 24-hour journey if you go via Alaska. And you come back by the same route. I mean, towards the end, I mean, we were overflying Russia, but certainly at the start, we were in polar country. Very interesting time. During the thrashing out of those agreements, I learned a few things. I mean, I arrived at Fujitsu for the first time to deal with these detailed agreements, and I walked in with my camera. I didn't walk in with a camera to take some photographs. I walked in with it because I didn't think if I left it in the hotel it would be there when I went back. And anyway, security removed it, put it in a box, and kept it there till I was ready to go home. I happened to say to Fujitsu that, you know, like, remind me to collect my camera from security. And they went, oh, why didn't you leave it in your hotel room? I said, I don't trust it. You know, in England you couldn't do that, in America you couldn't do that. He said, when you go home tonight, you look at all the railway stations and see all the thousands of bikes that are all left standing up outside. There's not one of those got a lock on it, and nobody will ever take the wrong one. The following day they came in with all sorts of statistics about crime rate in Japan. This is not crime between gangs, this is crime on private individuals. And incidents of murder and things like this. And there was like one murder in Tokyo for every 6 minutes of New York time. And they gave all these statistics in terms of New York time. They're absolutely unbelievable. After that, I left everything. They said, if anything gets stolen from your room, we will guarantee to replace it. Of course, I never lost anything. I mean, there was another time when we were doing this contract, this manufacturing supply agreement. We did all these production cubes and we were doing the pricing, and we'd got this agreement signed, and that was the toughest one to get signed. And I'm due to catch an aeroplane, and I said, right, tomorrow then I'll come back in, and then I've got to leave and go fly on this aeroplane. And they said, oh no, you don't have to leave. Well, I'll the aeroplane up for you. I said, you can't do that, it's British Airways. And he said, we can. And we did. Anyway, the following day I went in, and they then produced some more sheets with the contract which I'd already signed. And they said, we'd like you to sign these. And I said, well, why do you want me to sign those? He said, well, somebody in our accounting department made a mistake. And it should have been cheaper for you. So therefore, pages this, and this, and they named them, and they gave me them. They said, we would like to replace those in your contract. And if you study them, you'll find that all the prices are cheaper. And they were, they gave us about a 20% reduction. On all the prices, all we had to do was just initial those pages. I mean, they're just incredibly honest people. I was quite happy with the contract. They weren't. There was an error in it. Right, if we look at 2956 to start with, that machine, it was in Schottky TTL. And then that moved to 2966. So that was the S2 machine, which was 24 logic beats per instruction on average. S3L, which was 2966, had 12 logic beats on average. And the clock speed had improved from Schottky TTL to Metal 10K by a factor of half. The actual time had halved. So 0.33 went to times 1 in performance terms. When we came to S3L, we shifted the number of logic beats down to 7, and we improved the clock speed from 8 to 28. So S3L was actually 5 times more powerful than a 2966. So we've got 1.8 factor in functional improvements and 2.8 factor in technology improvements. And the technology improvement was just simply getting that FJMB12K as opposed to Metal 10K and getting the 28 nanosecond improvement. Functional improvements, we built 3 separate mills, an address mill, an arithmetic mill, and a check mill in. We lengthened the pipeline, 2-loop scheduler, single beat slurring, and we built it all on 6 MCCs. Now, development route, this is absolutely critical to us and crucial for the same reason that John said. We do not want any remakes. Remakes are expensive. I mean, to remakes, if we had to redesign a chip, not only would it throw the prototype timescales out if we got it badly wrong, but it also meant that we had to spend about £100,000 on making a new set of chip masks. We didn't want to do that, and I've certainly not got it built into my budget. So the aim was to minimise the design faults, shorten the development timescales. So what do? We evolved it from 2966. It had a very rigorous top-down design structure. So we designed it at a high level and then worked out progressively in various design levels until we got right down to the gate level on the chip. So we had to have excellent functional and physical partitioning. We knew exactly where all the boundaries were. We rigorously audited the design at all its stages of decomposition. Dedicated design automation machines, a whole floor of them. The design was controlled and captured on a database. We had very good design tools for checking the path lengths and the timing, and for checking the noise, because at these sorts of speeds you get crosstalk between tracks, and we had to be able to control that as well. Design had to be fully toleranced, and the chip designs were validated by 2 simulators, as you'll see. The functional design was validated by SOL, which is simulated at unit level. So we knew that the functional design of the system was right, and we could run the microcode on it, and we could actually run VME on it, all by processing this through 2900 systems. So we then, detailed design was validated by Fujitsu simulator, where we sent certain diagnostic patterns through, and on their machine they were able to run our diagnostic patterns and get the answers we got. And we used the pilot to validate all the development route and the software tools that we built and they built. So the DA activities were at a graphic level. We captured all the units, all the high-level designs. We captured all the engineering diagrams, the MCC and side panel designs, and the microcode design. They're on graphic workstations, so we have lots of those. Got some 2900 machines, which were doing the high-level logic design, doing all the logical and physical mapping, and doing all the simulation that we needed. About 1900 systems that were doing all the test generation and diagnostic generation. We had the M190 system that was doing chip designs from these graphics units, doing chip tracking, all the placement checks on the side panels and MCCs, and doing gate level simulation and comparing all the answers to the answers we got when we ran our unit level simulation, doing delay analysis, and noise checking, and then we sent everything over to Japan, where they did the tracking and produced all the production information, but then fed back from that tracking and all the production information into the design systems in West Scotland, all the actual physical lengths of tracks, so we could check all the timing out. So that was very crudely what we did. Design stations were taking in all this input, including the microcode and all the flowcharts, because it was necessary in order to be able to run everything, to have that. That was fed into a VMEB service, which has got the simulated unit level tests on the microcode, all running on this VME machine, which is now producing simulated unit level test patterns and simulation microcode. And a George 3 1900 one that was generating all the engineering systems, all the system diagnostic generation. This machine was doing all of the tracking and producing rework information, delays, noise tests, any printed circuit board errors that it detected, and feeding all these things back into this for terminator replacement. It all then shipped over to Japan, production information. We got all the track length feedback once the chips and everything were tracked for real. So it was a big interactive system, and it worked extremely well. So we actually achieved, we now changed to mainframe systems, you'll notice. We achieved 11 million instructions a second compared to IBM. It was computer room and environment, so we didn't need any special air conditioning. It was a stainless steel cabinet, so we've gone away from these, do it with 10 coats of HJ Mulliner, Rolls-Royce finish, all things like that. Typically one of these systems had handled between 1,000 and 2,000 users. It had have, as John pointed out, either 8 or 32 megabytes of store per node. If you compare that to my PC at home, then mine is ridiculously tiny. That's main store memory, of course, but I mean, it had 3 local area networks and 6 macro LAN, which were fibre optic networks. 120 chip sites, got a node support computer, which is for maintenance of the system and for telediagnostics and all of those things. So you dial into these machines and repair them remotely. And we've got a multiple optical fibre interface for connecting together multi-processors. It's very compact size. It's 6 foot high, 4 foot wide and 28 inches deep. I haven't bothered to put the other measurements on. I still think imperial. Weighed in around about 1,000 pounds. Air was fed from the floor at 15 degrees centigrade. The whole thing dissipated about 6 kilowatts, and that was dumped to the room, so the room air conditioning extracted it. Environment was anything between 15 and 35 degrees, it was acceptable, and humidity 35 to 60. All the electromagnetic emissions were to international German and US standards. Noise was 58 decibels, and we met VDE, CSE and UL approval. That's what a box looked like. That's 6 foot high. The power supplies were in the bottom rack. Inlet air came through the floor and it came up this end duct. It went into the power supplies, into the cube, into that blower unit where it would push up vertically through the infrastructure motherboards, the memory and the I/O controllers. The cube went through that way. It had three assistance fans pulling air through, and I was exhausting it up that air duct there. And the AC control was here. And all in a, when you can compare that to what Fujitsu had done with their cubes and what they built with their cubes, when they came and saw that, they were absolutely amazed. They'd taken 3 cabinets and everything in order to do that much. They hadn't thought of splitting it all separately and joining it together like we did. That's what it looked like. It's taken from rather a low angle, as I said before. We built it first of all in steel and then decided, well, structurally stainless steel is a lot better, it looks a lot nicer, people think they're getting something, so we actually did it in stainless steel in the end. And it all came out shiny and glossy and beautiful. That's the node support computer you can see there. Those are all the boards carrying the input-output memory. That's the cube, these are the side panels. Power supplies all hidden in there. And that was a node. Now Fujitsu also, as part of the collaboration deal, gave us special probing tools. Well, they didn't give them to us, they sold them to them. They were a mandatory part of this technology. I mean, the technology was so good that they had a tool for everything. And all of these tools were specially designed. So they had a side panel prober, a special thing that probed the side panels. They had point probers, they had LSI probers, they had RAM probers. So you could actually probe down onto anything and measure its characteristics. They had resistor pack probers, tie-up pins, extension cards, and everything to do it with. And all of this was immaculately engineered equipment. And I mean immaculately engineered. They also had some other rework tools for doing repairs and modifications, such as the MCC, we had automatic wire bonding machines. Take an MCC out, we could program where we wanted wires to be put, and it would actually do it. And it had actually removed components, it had removed tracks if we asked it to. It would, that was quite an interesting device, that Voltamp curve tracer. The program actually knew, the software, knew how many inlet gates were connected to this particular track, or how many outlets were joined together, or whatever. And it predicted what the impedance would be and what the capacitance would be over this length of track. So it probed it and actually plotted curves and said whether they were right or wrong. So you could probe anywhere without the power on and actually get all the characteristics of it, and it could tell whether there was anything wrong or anything shorted. Actually, an amazing piece. I mean, I hadn't heard of that before. And we had a clock tuning station where you could actually set the clocks accurately across all the boards. And then for the side panels, you could bond the things on it and remove them and do it. And this was all automated equipment. We had a room for it, didn't we, John?
Yeah.
And that's typically how we connected these things up. We trying to look where I'm up to now. We followed right up there, new work tool. Right, well, in order to provide resilience within the system, and in order to provide expandability and to allow us to get higher performance, we connected nodes together, like that shows 4 nodes, and we connect them to a macrolan ring. The macrolans we use for attaching magnetic devices to them. Those 4 shown there are disk controllers. Typically, there'd be 4 disk controllers on each ring, and we could have 5 Eagle 2 disks on each controller, which would be 25 gigabytes. 12.8 gigabytes was the average on each ring. But if you had low usage files, then you could collect up to 16. So various people, depending on the size of the file store, would have different configurations. The whole system, each node had got outlets for OSLAN, Ethernet, providing all these comms gateways, printers and terminals which you can connect onto. There were macrolans for all these disk and tape activity, high-speed magnetic tape. We could have retained disks on. Notice all these things have got CAFs on as well, so all the content addressable files stored. And we've got this wonderful interface that connects nodes to nodes. And that is purely in order to keep the software, because we want this system, which has got, that's showing 2 nodes, actually to retain in sync, and for it to appear that there is only one version of VME running. Although VME is running in each node separately, the 2 versions of VME have got to communicate with each other at high speed. Oops. So that all the storage is synchronized. If this processor wants to access something and that processor is just written to, you've got to update the memory within that node before you do it. So that's what all that very high speed link was about. That was a multiple fibre optic interface, not just a single fibre like the macrolan was. It was a private communication channel between disks. So the whole system was scalable. Simply by adding nodes, we could scale the performance with the effect of only one version of VME to any user. It was also resilient because one of these nodes could fail and the performance of the system would gracefully degrade because all the file store and everything and all the terminals remained available to the nodes that remained in the configuration. So you could just go and knock the power off on a node and it would just gracefully degrade. So it was a way of achieving resilience and a way of getting scalable performance. And you'll notice here we've also got cross couplings from these high-speed disk controllers that allow that disk controller to have access to both those disks. So if that one controller breaks, we've not lost any of the information on that disk. So we have all these things all over the place. I mean, those macrolans meant that we could still retain full system performance even if these disks were mounted 2 kilometres away from the processors. So there was a 2 kilometre macrolan away from the node. So several of our customers, did actually put the whole of the disk storage in a different building. Vodafone was one example. They did that. British Gas was so concerned they put theirs down a mine underground, so that the jumbo jet landed on it and sort of wipe out their file store. And they had nodes in different places, so these nodes were moved apart as well. So you could have half a kilometre between the nodes. So several customers had the nodes half a kilometre apart. And the macrolans 2 kilometres. There was immense flexibility in that system. So if we look at the benefits that that gave us, not only in terms of this scalability and resilience, but it also allowed us across, because DM1, all these things called level 15, 25, 35, etc., all the ones in yellow, there are 2 different, that's a 4-node configuration of DM1. They all fitted in. They all had the same interface for peripherals. They all used macrolan and oslan. They all used the same version of VNA. So we're able to provide performance spectrum. I mean, the green ones are S3L, and they go down from here up to there. Yellow ones are DM1s, all the same design. And the yellow ones happen to be Essex, which is the next machine on the range. But the whole thing is a common VME system right across the range and a common set of peripherals. So people could just upgrade their processor system. They didn't need to upgrade anything else. So we exploited this business of being able to, like, that's level 80, that one there. And you'll notice that we've gone above it with the same machine and we've gone down below it, so the level 45 with the same machine. So we're able to slug the microcode. So that is the same machine as that one. It's a single node, but we've reduced its performance. As that is a reduced performance one, as that is a reduced performance one. We sold those systems at a lower price than obviously the full performance version, but we were then able to sell them a golden wires upgrade, for which they gave us a fortune, and we just gave them a different version of the software. It's a different version of the microcode, really, but didn't have the delays built into it. So we made a complete range out of these systems. That's the DM1, the thing John was talking about. That's the voltage cabinet. That's a level 80, and that's Essex. By the side of it, Essex is the later machine. Now there's an interesting slide. It shows that S3L has got a 15:1. Oh no, it's that one. That one shows that S3L's got 15:1 power range using the same design. when S3L was launched, called S3L this time, that's how Fujitsu christened it. I rather like the name. That's a dual, that's a triple, that's a quad. That's 1,000 mil performance indicator units. We were now getting into bed with the Gartner group and persuading them that ICL was better than IBM. And they actually published many articles to their IBM clients extolling the virtues of VME and the designs that were produced. And they claimed that at the time we were at least 2 years ahead of IBM. So that happens to be conveniently a Gartner number of 1,000. At the time, that was the nearest IBM single node. So we were way ahead. At the time that S3L was launched in 1985, it was the world's most powerful single mainframe. IBM, they cheating came out of the machine, so we had to go dual, triples and quads in order to go out ahead of them. I mean, we were able to do so. So it was pretty remarkable from that point of view. That's another one of these histograms that shows where things are. That's restricted to DM1s and S3Ls. Shows the 15:1 range, power range of VME with the same design. Various restrictions like level 45s and level 55s, these things are there. You're only allowed up to 64 megabytes of storage and 2 IOCs. As you get to level 65s, you're allowed 3 IOCs and 96 megabytes. When you got to a level 80, I mean, you could have 3 IOCs, not 128 megabytes, which seems a bit stingy by today's standards. And the other thing that was important to us in the whole of this, one of the reasons for everything being successful, were that we had Fujitsu engineers working for us in West Scotland. We had 3 principal Fujitsu engineers. In order to, we couldn't cope with the time difference in terms of talking and everything, and we certainly couldn't cope with the language, because most of the Fujitsu people, engineers, spoke Japanese and their English was not very good. Certain of the people were extremely good at speaking English, because, as I mentioned in John's talk, it was a qualification within Fujitsu that you're able to speak English if you're going to make any progress up and running a lot. So they had all their own internal training courses and everything, teaching people English. So at the time I was due to get these 3 engineers, before we had done the design of it, and my people had been out on that training course that I mentioned before. I said to all my people, right, rate the engineers you've seen, because we're going to get 1 technology engineer, we're going to get 1 design automation engineer, and we're going to get 1 systems engineer. I want to know who the best people are you speak to. So anyway, eventually Hiragori came back to me and said, right, these are the 3 people we're going to let you have. And I thought, bloody hell. Because he'd actually given me number 1, number 2, and number 4 of my list. And I thought, he's given me the best people, why? You know, I don't think I would have done it the other way around. And he said, well, you don't realise this. They want to improve their English. You know, sending them over to you is a big bonus to them. It will further their careers. He says, no, I haven't given you 1, 2, and 4. He said, I've given you 1, 2, and 3. You've got it wrong. So, I believe you. I'm not arguing. I'm just saying I was very surprised that you've done it like that. And we did get some superb people. So. And we made some really good friends out of it, because I mean, when these 3 people arrived in the UK, I invited them round to my house, you see, for dinner. And they walked into the dining room, which was laid out. A restaurant! It was just like anyone out of our dining room, but they got laid out quite like that with glasses on the table and several knives and forks and things. And anyhow, my wife served dinner and then sat down, and there was an absolute stunned, shocked silence. No female ever sat down to have dinner. Well, their wife didn't come out of the kitchen. Well, they literally didn't eat together. And I had to explain to them that, no, this is how we did it. And my wife was actually going to sit down and eat with us. And in the end, they accepted it and started jabbering again. But I mean, they didn't like it to start with. Most peculiar. But they accepted all of that. The thing that taught me the most, and I'll talk about this before we go on to talk about why ICL was so successful, because these three guys, Mackie, who was the design engineer who worked for Hiraguri, was the most important one. Yoshi and all the technology, and Kim did the DA, and all three were extremely good. When Mackie first arrived, he was the first one to arrive. He came in on an aeroplane from Tokyo into Heathrow and flew down to Manchester. This was on a Friday, and everything got delayed. And I had to send the company chauffeur to go and meet the plane that was coming in at Manchester to get him to bring Mackie back. It's now about 8 o'clock in the evening, and I'm the only person in West Scotland apart from the security staff. I'm waiting for this Japanese guy to come. He arrives, and I said, "What do you want to do?" So he said he was tired and he wanted to, because we'd got a sort of flat for them. So I arranged for Victor, that's the chauffeur, to take him to his flat. I said, "What do you want to do tomorrow?" He said, "Play badminton." I said, "Oh." I mean, we had badminton players in West Scotland. We had a badminton team. I said, "Well, I can't contact them for you now. So the best I can do for tomorrow is my 15-year-old son can play with you, provided you don't mind playing with a youngster." He said, no. And what I hadn't told him was Richard played for Cheshire. So I went home and I said to Richard, "Right, you're playing badminton tomorrow, but what you've not got to do is slaughter this poor guy. Remember that he's just come from Japan. He's, jet lagged and he's everything, and you've got to treat him gently, because after all, he's, somebody we're collaborating with him, very important." Richard said, "I can't play gently. I've got to play a normal game." I said, "Richard, play gently." So I took Richard to this badminton court. We met Mackie and they went in. And I went back an hour and a half later, and Richard looked like a wet lettuce. And I thought, I said to him, what happened? He said he thrashed me. He told me not to play well. So on the Monday, when I went into West Scotland, I said to Mackie, "I believe you're quite good at badminton." He says, "Yeah, I'm the current champion of Tokyo." So yeah, he was quite good at badminton. But I then apologised and said, "Well, sorry, I only gave you a 15-year-old. And he then said, I want to carry on playing with Richard. Don't want to play with your badminton team." He said, "Because Richard's on his way up and I'm on my way down. And the longer we play together, the sooner we'll intercept." Which was really quite good. And the big lesson that came from that was when Mackie's family came over, we took them out, his wife and his 2 sons, as it was then, and myself, my wife, and our 3 sons. And Richard was fiddling with his parcel, but he was going to give Mackie a gift to say thank you for teaching me all this badminton, because Mackie taught him an awful lot. And Mackie also taught him how to string a badminton racket manually, which was something the county said is unforgivable. You never do that. What you do when you break the racket, you bring it into the county and we'll restring it with a machine. So Mackie disagreed with this and said he could string a badminton racket better than a machine, which he promptly did. Richard took it to county and they tested it and were amazed how good it was. Richard was then taught to do it to the same level. So Richard owed him a big thanks to Mackie. So we went out for this dinner, Rich was fiddling with this thing, Mackie called me over and took me outside and said, "Is that a present Richard's going to give to me?" And I said, "Yes." He said, "I don't want him to." He said, "I've got a present to give to him." I said, "Oh." I said, "Well, why are you giving him a present? He wants to give you one to say thank you for all you've done for him." He said, "You don't understand." He said, "In Japan, if you were ever taught a manual skill, you have to pass it on to at least 2 other people. And you have to be sure that they have learnt it properly." He said, "Richard has half fulfilled one of my obligations. I have to give him a present." And we agreed to swap over. You know, Mackie was very reluctant to agree when he wrote it was their own, and Richard would give him a present as well. But I mean, that taught me so much about the Japanese culture, and particularly about negotiating with them. Whenever we came unstuck, whenever they came across a blockage, you had to invert it and think, you know, what way are they thinking? Is there an opposite thing that you can do? Because I never thought of there being a thing in Japan where, you know, it would be something they would give a gift to somebody they spent time with teaching to play badminton and street badminton. So all that was a most valuable experience, actually getting to know the people. This is why I think the whole thing turned out so good. That's a picture of Hiragori. He was made a member of the worshipful company of IT of Freeman of London in 1992. And there we can see we're doing this engraving of London Bridge, etc., etc. We got sheep over. That's a picture of 1988 with Baby, obviously showing Chris Burton, Tom Kilburn, Patrick Green, who was the director of the museum, Michiona Russo, and myself. The interesting thing, the reason I showed it to you, just shows the dedication of the Japanese people. He made a one-day trip from Japan, purely to be at that anniversary. Sorry? Yeah.
1988.
40th.
Sorry, yeah, all right, sorry. It's not an error, I know. But I mean, it's the fact he made a special journey, flew from Japan, came to this event and flew back again, all in a day. I just think that's incredible. You know, they would be bothered to do that. And he looked quite bright and cheerful there. That's a picture of me with Mackie. That's the picture that was on the website for those of you who lived. 12th of July 1985. So this is champion of Tokyo at badminton. And so why was ICL so successful? Well, I mean, the UK was very good at ideas and designs, and we did develop a first-class development group. We had to have a first-class development group so that we could get the design right first time, and we were not going to have to bear lots and lots of rework costs. Fujitsu were absolutely excellent at technology and excellent manufacturing skills. But the big thing in their favour was the cube design. And the STL project, we were like absolutely determined that we were going to. We got this impression of Japan as being people who worked extremely hard, and we were going to equal them in terms of endeavour, we were going to equal them in terms of pride and determination. We're not going to be big about it. And then I get this complaint from everybody who were working too hard. Well, no, it was a tremendous team spirit at West Gorman in this era. And of course we had the advantage that we've got 3 Fujitsu board directors championing this project through Fujitsu. So this was in a way, in terms of Fujitsu, they were the 3 who put the necks on the block in order to sell this to ICL, in order to do it. And they all were extremely supportive. And, as you've heard, Eric Gorey gave us his 3 top engineers to work in West London. And we're still friends with all of them. I mean, we still exchange Christmas cards, we get regular emails and everything from them. So, it was all true friendship, cooperation, there was understanding, there was a trust, the families met the families and everything. There was a pent-up demand for a new machine in the ICL customer base. They'd gone, like the normal cycle had been 5 years, and they're now 8 years down the track without a new machine. And the Inland Revenue and the Heineken Steering Group, which was our club of all our most important customers, including the DSS and British Gas and all of that, were extremely supportive of what we were doing. But the Inland Revenue in particular were spectacular. And when we were doing this, I got invited to Somerset House and went through all the plans with the Inland Revenue. And they said, right, we support that, that's what we want. We will help you validate this machine. We'll give you 1,000 people to work on the validation of it. And they did do. And Steve Matheson, who was Director General at the time of the Inland Revenue, said, I want this project to come good. If it comes good, it's going to mean that I achieved my objectives a year early. So Steve Matheson achieves his objectives for the Inland Revenue, which is to get the Inland Revenue computerised. So he said, I'm prepared to put these 1,000 people in to do it. Are you prepared to work with me? I said, of course I am. I said, all you've got to do is ensure that within ICL this project remains constantly funded. He said, well, I'll go and see Peter Bonfield, he said. And I'll tell him that they're going to lose the order if they don't. And the order was for the first year of 58 S3Ls. And the Inland Revenue had a lot more eventually, but I mean, the Inland Revenue were the ones who I almost at the end felt I was working for. I had promised to them that we would do it, and we were bloody determined to do it. Just like we were determined, you know, to work well with Fujitsu and not let the UK down, we're equally determined we're not going to let the Inland Revenue down. So I mean, my friend was Steve Matheson, and again, somebody I still keep in contact with. So what were the performance factors? Well, nodal architecture, as you've already heard, scalable, resilience, so all the mainframe attributes, reliability, maintainability, high availability, high security, because it's got a VMA operating system, it's got a common set of peripherals, it's got Fujitsu technology, which is 4 times better than anything else available in the world at the time. We got down to a 25 nanosecond clock, the proprietary macrolon, which allowed us to separate the nodes and to separate the disks from the nodes, build up this scalable system, was absolutely essential. CAFs was another major attribute, which gave you all your file searches offline. We were able to use one design to get many models, the multi-nodal slugs. We've got an outstanding and a very experienced design team who had designed machines before and been through all the RSI work that we were building in the car park at Westcott. And we ended up, after the original target of selling 400, we sold that, which is what we based our negotiations with Fujitsu on. We sold over 1,150. So we outsold the target by a factor of 3 almost. And a consequence of that was we based the price on 400, and then we did the negotiation with Fujitsu. If we sell another 100, the price comes down by that much. If we sell another 400, it will come down by this much. We were at bloody selling prices for the last machines. And we did do. And we only, of the 120 designs that we've done, 6 of them had to be remade. So ICL had 5% chip changes, and none of them were showstoppers. In other words, it's slightly sluggish performance, but we could bypass it all by microcode. So it didn't stop us completing the design, it didn't stop us doing anything, but we remade the chip just to get the maximum out of it, which was a brilliant performance because I actually budgeted for doing 20, but didn't talk into one for a lot. We made 5% errors, if you like, but they weren't showstoppers. Fujitsu made 25% errors in chips in their machines, and they freely admit to that. So they ended up buying our DA systems. Before the tape was over, they bought our DA system off us so they could use it for their next machine. So mainframes made a bit of profit out of that. Armdal, 100% remakes. And Fujitsu just referred to them as a sloppy bunch of Yanks. Some of the STL design team at Alder Edge, you might recognise some of the people there. That is Yoshi, who's the guy who replaced Mackie. Peter Fairfowl, John Allenby, Jeff Hopcroft, Chris Shaw, that's Hiragori, Brian Proctor, myself, Vinny Needy, David Dace, and Graham Aber. And that was in 1992. That was after Hiragori had come over. Just to show you what level 30 technology is, because John had one of these slides in his thing. That's one of the printed circuit boards that ICL produced. These are very little daughter cars with memory on. Those are the C8K chips, which you can see in sites like there. And that again was air cooled. This is just attempted because there are presentations beyond this one which show you what we did for Essex. Essex, as I said, was the next machine after STL. 90 minutes processing power compared to 91 for Armdal compared to 81 for IBM. And you can see the difference in weights. We came in at 1200 kilograms, IBM 14,000. 3 square metres compared to 20 square metres, 15 kilowatts of input power compared to 88. We've got 2 nodes, they've got 4 CPUs. They're shunting out into the room, or into the air conditioning system. It's the cooling system they had, which was liquid cooled. We can do 14 kilowatts. Armdal using the same technology, 37 kilowatts. And again, 80 kilowatts. So we were rather proud of that. I've put this in so we can show a picture of Virgilio. There's Virgilio. We had a mainframe engineering achievement dinner, and Naruto awarded medals. You see some well-known people there, like Arthur Humphreys, Peter Hall, Colin Haley, there's Brian Proctor, there's Brian Warboys, Jeff Hopcroft, Keith Todd, no, who else?
George Felton.
Oh, there's George Felton, yeah.
And Graham Aber. No, Jeff Hopcroft.
Jeff Hopcroft there, yeah, I mentioned Jeff. Oh, do that one. That's the Essex first prototype. Again, just showing some of the team there with Essex. That's got the correct date on it. 50 years of progress. Now, we did this, we presented this slide, or had it available for the birth of the baby. So when the baby was first produced, we raised it at a factor of 128 bytes of memory, 4 kilowatts of heat output, size you can see, weighed a ton, made out of vacuum tubes. What trimestral looks like in 1998, it was 25 billion times the performance. It's got 8 gigabytes of memory, which by today's standards is trivial. Its heat output was 2 kilowatts, so it was half the heat output. It was an eighth of the size. It was a third of the weight, the technology was 200 million times better. And that's the progress of two machines, both designed in Manchester, over 50 years, from 1948 to 1988. And there are stories behind all of these, so I can tell you all about Trinetra and Essex at some future day. How many more of these are to go? No, that was too complicated now. Right, that's the end. If there are any questions, John and I would be delighted to answer them.